a discussion of the Pacific Ocean plate, part of the discussion of tectonic plates of the Earth. Firstly, plates are outlined by earthquakes for a large part, and the Pacific Ocean plate, of course, is surrounded by the so-called Ring of Fire, and probably 75% of Earth's earthquakes occur in that region. However, the Pacific plate does not cover the entire finally to come north through New Zealand up to Samoa and out across the northern edge of Papua New Guinea, through Japan and up to the edge of the North American plate on the Aleutian Arc across to Alaska. It then follows the coastline of North America fairly closely and is part overlapped by the continental material of North America. This is an outline then of the Pacific Ocean plate, the red boundary where it is shown extending south from British Columbia essentially. It's overlapped in the area replaced by the transverse fault, the San Andreas fault, and the plate boundary comes down through the Gulf of California and out towards the Galapagos, and as described before, swings around all the way towards Macquarie Island, south of New Zealand. Most of that eastern and southern boundary is effectively a diverging one, separating with creation of ocean crust. That's the reason the Pacific Ocean plate is essentially moving west-northwest at 95 millimeters a year, equivalent to 95 kilometers every million years, which is quite an appreciable rate for the largest plate on Earth. So that red portion of the plate boundary is the spreading ridge of the Pacific Ocean. Another view of the earthquakes shows, in fact, that the spreading ridge zone, at least through the Pacific, is not remarkably identified by earthquakes. It's quite clearly shown here, but it's the subduction zones of the west running from Macquarie Island north to Samoa, across effectively the northern section of Papua New Guinea and up through either Japan or the Marianas Trench, if you take the eastern boundary, Kurill Trench up to the Aleutian Trench and across to Alaska. So enormous number of earthquakes occur along this zone due to the subduction of the Pacific plate because of its north by northwest, by its west by northwest direction of movement. This diagram illustrates as a sort of areas indicating the number of earthquakes of a particular magnitude, 9s and 8s, which occur very infrequently, perhaps once a year. Not a 9, certainly. It's almost a lifetime example to get a 9, as we've had recently in Japan. But you get 18 a year of magnitude 7, and you're right down to 6,000 or more of magnitude 4, which are the ones we would largely experience and notice in the capital cities of Australia. So the Pacific Ring of Fire volcanoes are remarkable. Every red triangle here represents at least an active or dormant volcano known to have erupted in the last 10,000 years and likely to erupt again at any time. So they're particularly dense along that western subducted edge of the Pacific Ocean plate. Here again is another more or less satellite view of the Pacific plate, and it does show the remarkable Hawaiian Ridge and the Emperor seamounts that run away from effectively Midway Island north to the Aleutian Trench. Those are extinct volcanoes carried away from the Hawaiian hotspot by the movement of the plate. So it's clear that something like 42 million years ago, there was a change in direction from north by northwest to effectively west-northwest, as is today. That trend just mentioned is the Hawaiian Ridge, and of course, the point that's now lying over the hotspot is the Hawaiian Islands. There are a series of other hotspots which offer pretty much the same story. Though we notice here that the Marquis, Samoa and Caroline seamount ridges are not as remarkable as the Hawaiian Ridge at this scale. To the south, there's yet another, of course, which is would just be off diagram on the Kermadec Trench south of Samoa. In the east there, the Cocos Plate and Nazca Plate, and in the far north, Juan de Fuca Plate, are actually the eastern half of the Pacific, or all that's left of them. The Pacific Ocean, that is the midline or central spreading ridge, shown in red, and the North American plate has effectively moved halfway across the width of the Pacific Ocean, because that is the central ridge where the spreading continues to occur. The general pattern of Earth's great recycling of oceanic crust is the origin of new crust at the mid-ocean ridge. They're shown on the right, due to upwelling of heat, probably coming 3,000 kilometres or more from the liquid core, or the extremely hot zone of the Earth. The convection currents in the relatively hot mantle result in movement of the plate away from the ridge, or tension, which is invaded by the volcanic rocks that create the new oceanic crust. But as the plate moves to meet in contact with the plate margin against a continent in the west, such as Japan, for example, the rather dense and cold oceanic plate will tend to subduct below the lighter continental crust, and the subduction creates a recycling of oceanic crust. So that in fact, the oldest known crust of the Pacific is something just over 160 million years. And that old crust actually occurs in the southern section of this particular view, the very western portion of the Pacific plate, diving into the Coral Trench under the, well, it's the Philippine plate, where the small arrow marking 4.8 centimetre a year is on the bottom boundary of this diagram. You can see there's a fairly complex pattern of plates here. In general, speaking about the Eurasian plate, we tend to talk of the American plate meeting with the Eurasian and the Pacific plate in the region of Japan. But in fact, there's a series of smaller plates, some of which are not shown here. The Okhotsk plate of the Okhotsk Sea region, which separates the Kamchatka Peninsula from the North American plate, is no longer considered to be part of the North American plate, but the Coral Trench and the Aleutian Trench, which goes off in an eastward arc south of the Bering Sea, are the boundaries of the Pacific plate. Here is some of that region showing Japan, Korea, and China looking north towards the North American plate, a very faint boundary going through Siberia, separating the North American plate from the Eurasian plate. There's a series of mountain ranges there which have resulted from compressional contacts between the two continental plates. The Kuril subduction zone swinging in right centre from the Aleutian arc swings past the Hokkaido in the north and the central island of main island of Japan, and swings south down a plate boundary which is effectively separating small triangular plate in the foreground that is the Philippine Sea Plate. And here's another view of the Korea, the Sea of Japan, and Japan itself, main island, that Kuril Trench, and showing the location of the Honshu earthquake, which was extreme, to say the least, and in shallow water. Hence, huge volume of water was lifted by the earthquake, and this flooded ashore as tsunami. It's altogether a collisional plate boundary between ocean and continent, although the continent of Japan, the small continental material, separated from the Eurasian plate mainland only 20 or 30 million years ago. The trench, the Kuril Trench, is very clearly marked on that Google image, with a few pimples of volcanoes sitting on the Pacific plate. This is the pattern of that subduction, red being the location of that destructive earthquake. It's in relatively shallow water above the trench, and therefore in a unique position to lift a huge volume of ocean waters, which then move like a droplet in a pond, but increase in amplitude as they come into the confines of the continental shelf and various estuaries. The deepest earthquakes well out in Japan Sea, the order of 800 kilometres deep, and show where the top of the plate is descending into the Earth's mantle. Volcanoes, the volcano trend or arc of Japan occurs roughly where the descending slab has reached 100 kilometres depth, and this is the base of the more rigid plate, and also the zone where introduction of fluids with the slab lower the temperature of melting, and magma develops, which rises to the surface as that volcanic arc. Just a picture here of the main island of Japan, Honshu Island, and Hokkaido, the northern island, showing the earthquake depths in colour, red being the shallowest, grading to orange. Or a subduction zone bordering continental material. In the south of the Pacific, we still have the Pacific plate effectively moving westward, slightly north of west in the northern portion. And this is subducting from the North Island, New Zealand, up to Samoa and around the Fiji arc and off the Solomon Islands, etc. There is an extension zone marked there for the Fiji Basin. Again, though, that expansion is in a sort of an east-west direction. Whereas along the North Island along the north of the island of Papua New Guinea, we do see a zone of collision, partly lateral movement, but it's a transpressional thing. It's moving laterally but pressing hard and building up their own Stanley Range, of course, while the Pacific plate slides by the northward moving Australian plate, Indo-Australian plate, in a transfer or transverse style fault. That movement at 90 millimetres a year is causing quite a concern as one gets to the east and the collisional zones. And here is that zone. We see translational faults or transfers, as they would be, because they effectively plate boundary across the north of New Guinea, and the Caroline Sea plate crosses into the yellow Philippine plate at that point, where that's in the Turkey's head of West Irian. And there's a fairly complex zone of subduction where the Australian plate's oceanic crust descending. The whole of the cylinder plate is a problem. It's being squeezed laterally from the collision of India far away, laterally to the east, whereas it's being squashed to the west by the Pacific Ocean plate moving west-northwesterly, not to mention the influence of the Australian plate moving to the north. So there's area particularly around the Banda Sea, the Banda Arc, and Sulawesi, which is not labelled there, but is covered by the term Eurasian plates, plural. Extraordinary zones of subduction and oroclines or bends in the mountain chains occurs, as one can see in the northern section of that Sulawesi island. Here's another rendition of pretty much the same zone. See the triangles for subduction with a small plate broken off the western section of the Philippine plate, the Caroline plate, subducting beneath the Philippine plate, which is also really part of the original Pacific plate. Then subduction under the Philippines, the Banda Sea subduction, and what has been a reversal of subduction at times, the Australian plate sliding in under the Pacific, as shown on this diagram. Again, this perhaps a little too confusing, but it shows the relative directions of movement, possibly in relation to the main Pacific plate, although the Caroline plate would not be moving 87. It's presumably in relation to Eurasia. So Caroline plate moving pretty much like the Pacific plate, which would be like 90 millimetres a year. But plates close to the Australian plate are moving at rates reflecting that 70 millimetre a year movement of our great mass of the Australian plate. And others are twisted and broken in the region of the North Bismarck plate. Again, also in the bird's head, you have irregular subduction zones and lateral sliding faults. Quite complex pattern. Again, perhaps simplified in this case, the western boundary of the Pacific plate is actually east of the Philippine plate, but it does have a huge influence in this Sunda region, where we see Sundaland block written. We have movement, northern movement of the Australian plate giving subduction under Indonesia, but there's also huge zones of subduction associated with the Philippine Trench and east of it, the Caroline plate, until you get finally to the westward moving Pacific plate. Looking a bit further at the southern Pacific Ocean, we have this trend of translation coming easterly from Papua New Guinea to Samoa, and then it turns suddenly southwards to New Zealand from Samoa, and strong subduction in that trench, Kermadec trench running southwest, and one can see it intersecting the Louisville seamount chain, which is coming a long way, almost from the central zone of the Pacific central spreading ridge. If one follows that back, there's a certain change of direction there around the 40 million year mark, about where Louisville is written to name the seamount chain. But that boundary of the western boundary of the Pacific plate slides through New Zealand, such as Chatham Rise and the eastern part of the South Island, and the further continental mass to the south of that are on the Pacific plate, which swings down to the southwest through the Macquarie volcanic island, and then swings easterly as labelled Antarctic plate boundary, follows across the lighter coloured zone, which is central spreading ridge, marked by 2 arrows against the Antarctic plate, and it's finally against the Nazca plate opposite Chile, and it goes to the Cocos Islands and then northward into the Gulf of California. So that is the Pacific Ocean plate, which is only half of the real ocean, which of course includes the entire Nazca and Cocos plates, and further north against the North America, it's the Juan de Fuca plate. So that's a very pronounced Kermadec ridge, actually through the South Island of New Zealand. It's a transfer fault because it's transferring westward subduction in the Kermadec Trench to eastward subduction in the trench going south to the Antarctic to meet with the Antarctic plate. We look then from an Antarctic polar view. Of course, the Antarctic plate has been spreading by growth in the central rifts, all the oceans really, as the Pacific plate moves away, the Australian plate moves away, and the Indian plate, if you call it separate, the African and South American plates, Nazca, have all been moving away from Antarctica, which is getting new oceanic crust added where the light grey meets colours, and they get equal amounts of oceanic crust added in that way. So that's the expanding zone of the South Pacific, and the reason for that west-northwesterly movement of the plate. And likewise, Australia's moving north from our boundary where the other black arrows are shown. Well, to go to the north portion of the Pacific plate, it meets with the North American plate at the Aleutian Trench and subducts underneath it. It then has a complex orocline or bend in Alaska, and the boundary comes down the western border of the North American continent. And of course, subduction of the mid-ocean ridge of the Pacific, which is shown here in a light blue dash, it's subducted obviously in the region of the San Andreas Fault, where the actual boundary is on land, making a section of Los Angeles to San Francisco on the Pacific plate, and also, of course, Baja California Peninsula. But a very broad zone of the Rocky Mountains extending to the Central Plains, it's 1,000 kilometres wide, I imagine, in places, is due to the subduction of the other half of the Pacific Ocean. So Earth's great recycler has moved at a pace there, as the North American plate has moved westward across that eastern half of the Pacific Ocean. And there's the picture now, although the plate boundary appears to be a transfer in the region of the San Andreas Fault, with the Pacific plate moving northward relative to the North American plate. But one can see how there's a relationship between the Juan de Fuca plate in the north and the Cocos plate, which is essentially part of it, presumably, and the Nazca plate, from which is separated from that main eastern half of the Pacific. And so much of that plate has disappeared by the westward movement of that North American plate. This is a picture of typical subduction cross-section of a region around Seattle and Vancouver, with the Pacific plate mid-ocean ridge. That's the Juan de Fuca ridge marked in red, dislocated several times by transfer faults, but the Juan de Fuca plate disappears under that would be the Olympia National Park region west of Puget Sound, northwest of Seattle. Likewise under Vancouver, the Juan de Fuca plate is essentially absent, and it's been overridden by the North American continent. And of course, subduction has resulted in magma formation at about 100 kilometers depth, shown by the pale purple spheres, and they're leading to magmatic intrusions, which give the cascade volcanoes like Mount Shasta and Mount St. Helens, the region south of Vancouver. Very significant danger from large earthquakes where the red star is placed, because these could easily result in tsunamis, which would effectively destroy Vancouver Island and sweep into Puget Sound and cause enormous damage in Seattle, one would imagine. So just reading this, the subduction zone on the western margin of the North American plate has swallowed some of the central spreading ridge of the Pacific Ocean, which is shown as a red line here. And it's been expanding for over 200 million years. I don't know that we can prove that, because the oldest ocean floor we know on either the Atlantic or the Pacific is only of the order of 180 million years. But suffice to say, we have only half of that crustal material represented, where the North American continent has ridden over it. So it should have a mirror image to the Pacific plate, which has got the zero age material being formed now along the spreading ridge in northern British Columbia, Yukon, and 40 million year offshore, getting to 80 million or even 180 million feasibly near the Philippine plate, where the mark of oldest ocean crust is given. So that expanding crustal material results in gradual migration of the plate, in this case almost westerly. So at the southern section in the east, the Pacific plate comes out of the Gulf of California in the north there, triple point with the Cocos plate, which is subducting under Mexico. Further south near the Galapagos Islands, there's a triple point again, and the central spreading ridge jogs its way down south to the of the Nazca plate, with two small plates down at that boundary with near the boundary of the Antarctic and Nazca plate. And then the Pacific rise extends out westward finally finding its way to New Zealand. So the red line is divergent boundary. The creamy colours are where the ridge is joined by transforms, and there's a particular reason for those, which is essentially the intersection of accurate lines with a global surface. It also accommodates rotation, any rotation of the plate. Suffice to say that the other plates on this plan are not involved with the Pacific plate, which is separating from the Nazca and Antarctic plates in this region. And that's another version of that, showing in more detail the green transforms and the red dilatory zones of the central spreading ridge. There's funny little plates, the Easter plate and the Juan Fernandez plate, quite anomalous, occurring down adjacent to the Antarctic and Nazca plate boundaries. We're not involved with the subduction under South America, which is incidental to the Pacific, plate, but the Pacific Ocean, of course, is growing laterally and spreading in underneath South America in a classic subduction zone. If we look at these coloured versions, we look at the bottom chart and we can see ages placed along that from 0 red to about 60 in the yellow, 80 in greens or 100, going to 140 in light blue and 180 in dark blue. So the only old sections of plate here are associated with the early opening of the Central Atlantic, about American plate over half of the expanding Pacific. And if we look at the Pacific Central Ridge coming out from North America through the Gulf of California and extending to the south past the Nazca plate, we can see fairly broad zones of relatively young basaltic crust. The crust that's 10 million years or younger is shown where the Pacific plate sign is offered, the brighter red, and we're just managing to see the 40 million year old crust at the very 9 o'clock position on this, and again south down near the Antarctic and complex plate of the Cape Horn region. There is some subduction going on there by the Antarctic plate, the only place anywhere that the Antarctic plate subducts is that small amount we can see at the bottom of this diagram. So this is the more or less classic view of the Pacific plate. One needs a microscope to read the rotational speeds or the relative motion of the plate, which is behind each of the arrows. They are proportional to the rate, and one can assume it's about 92, I think, up near the Okhotsk plate or Japan and far northwest. It's somewhat similar in the south, and there's not a great deal of variation considering the shape of the plate on Earth and the fact that it is rotating somewhat. So you would expect the speed in the north, speed of movement, a little bit greater because of the wider arc from its Euler point, or the point at which it rotates, which is presumably lying on Antarctica somewhere. The nature of the plate boundaries is illustrated. Blue is subduction, and you can see the directions of subduction marked by the little triangles. The complexity of the far west around the Caroline plate and the New Hebrides Plate or Fiji Basin. There's reasonable simplicity on the margin of the Philippine Plate north of that, and through Japan on the Kuril Trench and across the Aleutian Trench to Alaska. Very complex down the North American plate boundary, right down to the Cocos Plate. Thereafter, essentially spreading all the way around to the triple point where the Antarctic Plate, Pacific Plate meet the Australian Plate. Pacific Plate is the largest plate amongst Earth's tectonic plates. It's rather unique in that it's almost completely ocean, except for the South Island of New Zealand and Baja California. Both of these are continental grass regions, and they were originally on different plates in quite geologically recent times. The Baja California having come off the North American Plate in the region of Mexico, and the South Island of New Zealand having been on the Australian Plate and swung off originally as Australia and Antarctica separated. It swung off effectively from West Antarctica. I think we can rest at that point and call that a session, and question time can follow.